Alright, this video should cover a few subjects. We'll see how they blend together. It's going to start off as sort of a reaction or response to the Saturday Science Conference by the N whatever group. And they were attempting, I'll leave a link below, but I can't suggest the video because it's 2 hours, it'll hurt you. Attempting to have some sort of argument about the nature of redshift and the whether there's a difference between sound and light in terms of the function of the problem of redshift, if there's to say there's a problem. I've brought up before that they claim that there's a difference between admitting and receiving in terms of somehow it makes some sort of difference in terms of redshift. If the object is moving towards you, the emitter is moving towards you, or whether the receiver is moving towards the emitter, that somehow there's some difference in the redshift. And I would argue, I haven't seen any experiment demonstrating that, and it's just it's something stated by the mathematics, not something stated by a collection of facts, I would argue. And then the counter-argument is some relativity thing, like somehow you're defending relativity in the Einsteinian bullshit kind of sense, where everything's the same when it doesn't have to be the same, it just has to do with how we measure things. The broken ruler argument, which I think is clearly part of the argument. Anyway, that conversation got into a conversation about ether and all this, how these things move, and so I just thought I would throw in some suggested models for how the sound and then light function, because if you don't understand how they function, the rules of their function, let's call them, then how can you have an argument about whether or not it's a medium perturbation or something, whatever you want to call it. So I guess I'll start with sound. So I've argued that sound has to be created by a movement that moves faster than the speed of sound. That sound is a kind of reaction in materials, and it's not like you just have a gradual thing. I can go this fast, this fast, this fast, and it's all the same. There's a certain speed you get to where the rules change, and that's the speed of sound. That's why sound is so much more dramatic when things move the speed of sound, in terms of the distance it can travel. So the idea would be that something, in my opinion, has to move faster than the speed of sound. So it has to change its position from one position to the other faster than, let's just say, whatever the number is, 700 meters a second or whatever it is. And so it has to move faster than that. And when it does that, it creates a little sonic boom. That is, it starts to make the atoms move in a different way and create sound. So all sounds are just little sonic booms. So the more matter you move, the louder the sonic boom. So when an airplane goes faster than the speed of sound, it's creating a sound wave. It's not like the whole bunch of waves are compressed and then they're released. It's just that you're moving a big piece of matter, and therefore you make a big sound. You move a little piece of matter, you make a little boom. But it's all booms. And the sound is just changed in its tone through the process of going through, our faces, and creating echoes and distortions to the sound that change its tone. But it doesn't change the fact that the sound itself was a boom at the frequency of the sound, essentially at the boom. Going that speed meant you'll make these booms, and so anyway, if we thought about what sound is doing, the idea is there's a bunch of atoms in the atmosphere, and what we know is that when the atoms are close together, sound travels faster, and when they're further apart, it travels slower. So the more density, the more water in the atmosphere, stuff, humidity, the faster the sound travels. And it travels much faster in water and much faster in metals, let's say, because the atoms are closer together. But all these atoms are attached to each other, essentially. The electrons around the atoms are attached to the protons in the other atoms, even though they're not bound strongly. They're bound by the fact that they feel the nucleus of the other atoms, in the sense that they sense that. And yes, they're attracted to their own nucleus, but they're also attracted to the proton, and then they're repelled by the electron. So there's a sort of a balanced attachment, but they're sort of attached. Okay, they're not disinterested in each other. So there's a little bit of tension between them. And so now when you inject into that system a sound, movement, what you're doing is pushing those atoms into each other. So you're pushing electrons into electrons, essentially. And then they're repulsive, so they don't like that. And so you're agitating the system. But that agitation, if it's at a slow speed, you could sort of understand that the electron, the atom that's going to bang into another atom, they have this repulsive energy between them, the electrons, and that essentially the atoms are going to, deflect off of each other in, passive ways at regular speeds. They'll just say, at slow speeds, they'll just sort of drift into each other, towards each other, and then kind of just bounce off of each other, and there won't be any, it'll just be like heat. So the movement will just be heating, in a sense, the air by stirring it, by agitating the atoms a little bit more than they're normally agitated. But if you excite them quickly enough, so I just put a little red things for the proton, doesn't really matter, it's all about the electrons essentially. But if you hit them quickly enough, that means the atom moves in very fast into the other atom, and everything takes time, obviously, for stuff to, for it to know something happened. So there's always a bit of time lag between an action and a reaction. So the point would be there's a certain speed that if you push the atom, there won't be enough time for the atom to react. The atom will incur, because it's moving fast enough, into the other atom, and start pushing the electrons into the proton. So now it's pushing really hard against and it's really, the key point is pushing against the other electrons in the atom. So if the atom gets close enough, it starts moving the electrons, so they have a nice solid position. And when you start to move an electron, that means you pressurize all these other electrons, because they're going to feel more pressure as you bring this electron closer. That means you create more pressure this way, which pushes this electron, which pushes that one, which pushes, so they all push on each other. And so now you're kind of loading the gun in terms of getting a reaction. And the reaction is going to be that the atom is going to, they're not going to deflect off each other now. Now they're going to behave more like kinetic balls. So in a sense, they're going to bang into each other and just be exchanging that energy, because this atom now is going to absorb this incursion by everything moving. And so essentially, it's going to now do the same thing to another atom. It's going to bend into its electron pressure, and it'll just be a cycle of kinetic balls essentially going through the atmosphere. So I'd argue that they describe sound waves, they illustrate them as typical, the typical wave kind of thing, as if this is one solid feature of sound. And it's really not. It's really just made up of a bunch of these incursions, and they're all incursions that are coming out just like they would sunlight in a bunch of rays. And the adhesion of these molecules, like I said, the subtle amount of it that there is, might create some consistency, but all you have to do is change the thickness of the layers of the atmosphere. If you made this layer heavier because it's got more water vapor in it, this part of the wave will be way ahead of this part of the wave. So there's no obligation for it to be the same speed in all areas of the atmosphere. The thin places it can move slower, the fast places it can move faster, and it's really just about atoms acting like little particles, and it'll be atom hitting atom hitting atom hitting atom, and essentially in such a way that all the impacts are that you get no deflection, so there's no wasted energy in directions that don't matter. And the shear, like for any molecules that are kind of tied, molecules that are more than one atom and they're attached to each other, they're just kind of sheared off. They're hit fast enough where there's no drag, so they're just shear. So if the speed is quickly enough, then there's nothing to degrade the power of the energy, so it travels without being substantially degraded over distance by any other rule than the inverse square law, which everything traveling from a point has to obey. Yeah, that would be the thing that will, and the fact that the sound is obviously, with everything else, the sound is going over like a light bulb. Most of the light doesn't hit me. Most of the light goes there and lots of directions. So, you know, it can only hit what you place in its path. So certain paths only have this much energy. It's only a percentage of the total energy created by the thing making the sound. All right. So, but it's a physical thing, and it relies on a certain physical property. And there's no, what's a better way to say it? And so the speed limit, the fact that the sound doesn't go faster or faster and faster and faster, has to do with probably, I would suggest, it has something to do with this fact that there's a certain amount of distance between the proton and the electron, and the proton takes a little bit of time. You know, once you push on an electron, it takes time for the proton, to know you did that. There's a speed limit here of this time. So the proton doesn't know it has to move until a certain amount of time takes place. And so that's the speed limit. If you go faster, it won't do you any good, because the proton still takes a certain amount of time to know it has to move. So you can't accelerate the atoms any faster, because the proton won't know it has to move any faster. So if you try to accelerate the atoms too quickly, you might just break them. And you'll create radiation, you'll create light, you'll create some other kind of effect. This has sort of been demonstrated in some experiments. There's a little tiny shrimp in the ocean that snaps its claw really quickly. And it, so it's doing that in water molecules. And essentially it creates light, because it moves so quickly that it sort of breaks the atoms in the water and essentially creates some light. All right, so so if people people believe in an ether, if they think the ether is going to behave like air or like water, well, then they have to sort of concede that it has to have a mechanism of some kind to be doing this transferring. And if it's going to act, and it's going to behave so much like an ether, so much like water, and in a sense, when light travels, it does duplicate this to some extent. I mean, there's similar elements, very similar, even the speed limit part. But I would argue it's all there for a different reason. So anyway, let's. Okay, so now we'll do the redshift part, and then we'll go to light. So the idea is that if the thing that's making the sound is moving, it's going to, if it's doing something, let's see, in the direction it's moving, so it's making a sound that moves forward of it, that it's like it's dropping the sound, in the sense that it's it creates one of these vibrations at a point, and then it moves to a new location, and then it makes another one of those sounds. So obviously when it's moving towards you, it should be blue shifted. So I don't want to end up confusing myself. See, it does get confusing when you start going over it and trying to figure out, okay, which way is it going, and blah blah blah. So the one sound leaves, and it hasn't gotten as far ahead of where the next sound will be produced. So instead of it waiting, right, instead of this being at this position when the next frequency is dropped, it's at this forward position. So it means that the original number 1 is here, and number 2 is going to be here instead of back here. So you can see the frequency has been cut in half by this drawing anyway. So the first wave, or the first, so they need a better word, because this is really atom against atom against atom against atom. So the first knocks, or the first bumps, or the first whatever of the sound, moving at the speed of sound, gets to a certain location, and then you make the second noise. The pendulum swings the second time at this point that's closer to that location, which means the frequency, or the difference between these two moving forward, won't be the full length. It'll be something less. So you've shortened the frequency. So instead of things being this far apart, the noises are this far apart. And so that's blue shift, moving towards. So blue shift is clearly the physical universe will change. So blue shift isn't a measurement problem. It changes the physical world. It makes a frequency that's different. So it was making, say, 10,000 hertz, and then it's going to start making 1,500, using wavelength instead of frequency. Now, wavelength would be the length, yes, longer number. Frequency would be the smaller number. See, this is where they get it all confused. They just make it more confusing by having 3 different ways to talk about the period, the distance between. So, so you physically change the world. So the transmitter moving means the transmitter was, when it's not moving, it's transmitting 500. When it is moving, then it's transmitting 1,000 waves per second. So it's changed the physical reality. The receiver, on the other hand, it's, the 1,000 can be coming in, and if the receiver's moving away, let's say, it's going to convert that by moving away. It's going to provide extra time, because it's moving a distance, between when it absorbs it. So it essentially is going to measure it wrong. Something's going to have a certain 1,000 milliseconds between these dots, these waves, and it's going to end up converting that into 1,500 milliseconds between them. It's going to make them further apart, because it's moving away from them as they're moving towards it at a substantial enough speed to compromise. So that would be like half the speed of sound to create half the difference. But anyway, so in the case of the receiver, the physical reality is not altered, and all you're doing is moving your ruler. So you're trying to measure something while you're moving your ruler. So obviously your measurement ends up being wrong, essentially. But you didn't change physical reality. Physical reality was one thing, you're just making a wrong measurement. Where when the emitter creates redshift, it changes physical reality. physical reality is created by the emitter. Physical reality is measured, by the receiver. And so that's like an important distinction. And maybe that's why the math goes wrong, is that it's not recognizing that the receiver isn't measuring correctly because it's moving. So its measurements are wrong. It's that simple. And if you don't understand that, then you're going to get the wrong answer. So I would argue that there's, like I said, they're saying there's a difference. The math says there's a difference. I'm arguing if the math says that, then it's wrong. Okay, because there's no difference in the terms that as a practical matter, the receiver measurement will be redshifted the same amount as the emitter actually redshifted. Now, clearly, the waves aren't going to be changed by the bad measurement of the receiver, but it will receive it as if it was emitted at that frequency. So it doesn't change the fact that it's, from its measurement point of view, it will redshift it, change it just as much as the emitter changed it by moving. It's just that the change isn't happening to physical reality, it's happened to measured reality. And that's, it's a hugely important subject, this whole idea that you can't measure things in moving frames because your ruler is moving. Your measurements are always not accurate. You have to go to the moving frame, the frame where things are transmitted. I think I actually had a word for that. The transmission frame. But you always have to be in that frame to definitively, universal traveling frame. You have to make your measurements in the universal traveling frame to get an accurate description of reality. Because all the other frames, if they're moving, have broken rulers. Alright, so let's deal with the production of photons and their movement, I guess. Sorry I don't have this in the kind of order I want to. It's just that the subjects sort of overlap. Because this also gets into kind of conductors and why forces are created in the first place and what the nature of these forces are. What is electromagnetic? What is an electromagnetic bit? Wave. So again, it's called a wave, but in every respect it behaves just like, in a sense, the sound waves, like there's a bunch of things traveling at a speed. This, whatever this classic description of this medium of either the electric field or the magnetic field, it's some sort of field that in some way is irritated by what's called a photon. Photons are somehow a compression. Well, let's demonstrate in the sound thing, it's not really a compression, it's a movement. And yeah, you could call it a compression in the sense that atoms that were far apart are next to each other for a second, but they're only next to each other for a second, and they're just passing energy on. So it's technically, it's a compression. There's two atoms close to each other, but clearly what's happening is just a transfer of energy, transfer of momentum. And so apparently they have some description. I won't try to illustrate it because they don't have a real illustration of an electric field or a magnetic field. And so I would argue that the simple explanation for what a photon is just bits, like atoms, like solid things, like somethings, not nothings, and they're just at a distance. And so a photon is always made of at least two of these things. And these things are forces that affect electrons. So it's a force that is essentially the same force between electrons that creates their repulsion. So these force bits will cause electrons to move. They'll be absorbed and reflected by electrons. Alright. So you perhaps can create some idea of a medium through which it would be possible that the whole universe is made of these little bits at a distance, and all you're really doing is, again, banging one into another one somehow, through some disturbance. A piece of matter disturbs the field and makes these little bits bang into each other, giving the appearance of a movement. So the bits are already at some kind of distance. See, that doesn't really work. But okay, that would represent the speed of light. So they would be, this distance would be a way of representing the speed of light. But then you have to wonder how do you get different frequency going through, moving at the speed of light, when the frequency could only be made out of an amplitude of creating more of them or less of them. Well, how is that solved in sound? I'd have to go back to sound waves, and so I didn't really cover that. How does sound carry different frequencies at the same speed? Yeah, so that's probably something that needs to be added onto, and my brain's not connecting that one right now, so so this will be an incomplete video. I mean, really, it has to do with the speed of the vibration is different than the number of vibrations. Alright, so that's one thing to recognize. And the number is always much higher than the speed necessary. And so the so the frequency is built into the amount of time it takes for one atom to get to the other is slightly different. And so the frequency is built in to this component of distance and time. So the higher the frequency, the faster it gets from here to here, therefore changing the frequency of the event, because the event happens sooner. So this gets here sooner, then that wave will have a narrowness, and then other waves will have a fatness, and those are the differences in the frequency, is how fat, by how long it takes for the thing to travel that distance, it traveled. So you'd have to come up with the same thing for light, in the sense that the different frequencies of light would have to be based on creating changes in the speed of how fast you move an atom, and then having that be transferred by the standard distance to create slight variations in the individual not the time of the compressed part, but the time to get to compression. So the time it takes for this atom to get to here is the thing that's changing. So it's changing the distance between the things, and that distance is representing the different frequencies of light. But I'm still wondering how in a medium. Alright, well anyway, it doesn't, for the purpose of this argument, like I said, there are ways you can make it work with either an ether or without an ether. But I would still say the simplest, to make it simpler, would be just to say they're photons moving and not have to bother with this kinetic thing of where they all have to bang into each other, and they have to do it in such a manner that they end up with a straight line. Now see, sound waves, there's no obligation to travel straight lines. They don't have any precision. That's why they're doing something. Nobody ever uses a single ray of sound, because it's so sloppy. It's all over the place, because the individual molecules are all in different locations. They're not lined up in any way. And you'd have the same problem if you attempted to use an ether to describe light, because you have sort of the checkerboard problem. You couldn't, there's no arrangement that you could create that wouldn't create the problem of the diagonal distance being longer than the horizontal distance. And so you really couldn't have straight line paths like here. You know, there's no straight lines because they don't line up. And so if they don't have if they don't line up and they have to travel longer distances, some rays are longer than other rays, that's breaking the system. You know, if it has to go through more, if I have to hit through more pieces to go this way, then I have to go this way to go the same distance, then that's an automatic flaw because we don't see any of that in the real world. So there's no geometry that could still create photons that travel in a straight line using any kind of blocks, you know, because that they won't provide you straight line paths. Many of the paths won't be straight lines. It would be the point. So it seems that's a reason to recognize it's probably particles traveling through nothing, than rather something, you know, an agitation traveling through a medium, because the medium would have to be so much smaller than photons for it to have straight line paths. There wouldn't be enough straight line paths unless you made the medium insanely smaller, you know, of a density much smaller than photons. And you know, what's the point then? You know, how could you have that at the frequency of a photon? You can't have a very fine medium and then have them separated by the distance necessary to create the frequency, the consistency of the speed of light. So it sort of breaks down for that reason, I would argue. All right, so let's do a little bit of talking about why atoms have the same, why photons have a similar constancy. Well, to speed, it's probably won't be so. I mean, it's a speed just because that's how fast photons travel. So there's not going to be any physical mechanism that creates that speed limit. It's just the speed limit of how fast forces can travel. All right, but something that probably does need some explanation is the complexity of how forces that travel, these photons, when they hit something, like a conductor, what's happening inside the conductor is kind of important in terms of how is it creating voltage that moves through the conductor, and this effect where it's basically creating reflection. That is, it starts to turn into a magnet, and it starts reflecting the same force back, causing an increase in the repulsion in the case of like charges. Like when you move a magnet into a piece of copper, and the fact is the copper recreates the exact same charge, throws it back, and creates repulsion, and at the same time creating a current in the wire. So the idea would be is that these that the conductor, there's a couple of different features that you can sort of understand, that the conductor actually polarizes across its surface. So one side goes negative, one side goes positive, and that's for all the sides. So this side goes positive, this side goes negative. I mean, they're all around the circumference. And so in a sense, when you look at the conductor sideways, there's a plus side and a minus side in terms of how the force is coming off of it when it's magnetized. And it behaves as if it's a magnet, a compass needle going across the conductor, or a magnet, a plus and a minus magnet, however you want to visualize it. It has that appearance, so when facing each other, it would have the appearance of being a magnet in across its profile, however you want to describe it. And so clearly that's the magnetism that gets created. Now when there's no force hitting it, there's no magnetism. So that's a key thing to understand is, and when there's force hitting it at a constant, like if I put a magnet next to a piece of copper and I don't move them in quickly, I just move them to each other, there won't be any magnetism created in the conductor. It'll just stay copper. It won't react to the magnet at all if it's just sitting here. And it only reacts when this is moving. So there's a reason that the movement is what is changing the atoms and causing them to polarize for the time of the movement. They're polarized. And when the movement stops, the polarization stops. So that can sort of be understood that it's a conductor. So that is whatever polarization you change, however you change the atom. So let's see, we just use size as a way of describing the change in an atom. The conductors are very good at these atoms banging into each other and neutralizing their differences into averages. And so they go back to not having some sort of polarization. So if one's, this would say if it's big, it's proton strong. When it's small, it's electron small, heavy and sensitive. And when they're neutral, they're nothing. They don't act like a charge anymore. And so the idea of a conductor is that it makes these transfers really well. So whatever changes you make get erased quickly by the conductor. And so that's one thing to understand. But that still doesn't explain how, when there's a magnet sitting there, creating an imbalance in this field, and the conductor sitting there, it can't be conducting it because there's no current running through it. There's no changes happening. So whatever pressure is hitting it, somehow that pressure isn't affecting it enough to cause this idea of polarization. So somehow it has to move to create enough of an incursion to cause the imbalance. So I would argue that that happens. So when the atoms are on the conductor, and you affect them with a magnet, the fact is the magnetism is affecting the atoms, but it's not strong enough to polarize them. It's not strong enough to pressurize them. And it's only when you move that field, that is, you give it a little push in one direction or the other, that is, create more expansion or create more pushing in, that you change that balance between electrons and protons. So the atom have no forced to use the same colors, has the proton, again, is a distance between the protons and the electrons. And so again, the same sort of argument can be sort of made, that you have to move this magnet fast enough, okay, to move the electrons. Okay, so the electrons get moved to a new position, and it takes time, for the proton and even these other electrons to find their new position and then go back to being neutral. So at the moment you push, so if you sort of understand it in a, put the simplest way, there's a distance between the proton and an electron. So we just use a single electron, single proton. If you push this electron closer, it takes some time for that proton to know you did that. And the fact is that once you've got this electron closer to the proton, you've now created an ion in a sense. You've created something that as a whole, this atom, is now a plus atom, not a negative atom, a plus atom. Well, it's the other way around, actually. It's okay, I might as well do it the right way. Flip the paper over. Nope, used that already. I thought I had a whole bunch of extra pieces. I thought I did. Alright, so let's do this again. So the proton, and you have an electron, but there's always more than one. So the point would be is there's 2 electrons or something. But anyway, if you push these electrons in, you could sort of understand that they're going to obscure more of the proton, right? So the proton energy the light coming from the proton, when they were this far away, lots of proton light gets through, if you were to think of it as light. But as they get closer, you're blocking more. So if my hand's here, I can only block so much of the camera picture. But if I put my hand here, I'm blocking like a lot of the camera picture. So that's the idea. So when you push the electron in, you're essentially killing the proton part of the influence on the the proton influence is actually diminished by being too close to the electron. So the electron's closer to the proton. It's basically screening the proton's energy, creating a giant shadow, proton shadow. So it's a shadow against proton energy. The little electron is shadowing the proton energy. And so whatever force comes off of this thing now will be more electron force than proton force, because it's basically shielding the proton, ironically. And it'll take some time for this proton to realize these other electrons now have moved here and here. I should have done them in brown. So these are the other electrons. So these other electrons, when this electron moved, it pushed this one, which pushed this one, and this one was also pushed this way. So now they've moved, and they're further away from the proton. And so now the proton's going to react and move back to its position. So essentially, you don't need to create the magnetism doesn't need to be caused by some kind of current, but it can. The same pressure is created by current going through the atom. The same effect of pressurizing the atom, causing it to polarize, is created by current. But this one's being created by the actual force of a magnet pushing in. So when it pushes in or pulls away, like I said, then it makes the opposite. It makes a positive ion rather than makes a negative ion. It makes a if the North Pole is running away, then it's going to make a South Pole magnet. If the North Pole is moving towards, it's going to make a North Pole magnet, that kind of thing. A North Pole charge, a North monopole. So the atom essentially becomes a monopole in that direction, and it takes time for it to rebalance, and then once it does, it goes back to being a neutral atom. So it's no longer magnetic, it just goes back to being neutral. So it can only be magnetic, it can only be creating the magnetic field when it's in the process of changing. When the atom's being stretched, pulled this way or pushed in this way. So when the electron's moving in or the electron's moving out, that's when the atom is polarized, and that's when it's a magnet or a charge, and that's when it's going to create it'll act like a magnet for that period of time. And yeah, and so the effect is it'll reflect the energy that comes into it when it's polarized. So when it's polarized, an electron energy, so it has a bias towards the electron, it'll reflect the electron energy, more of it. And so then you end up with the energy getting reflected back and forth, and it recreates repulsion, because the energy just keeps bouncing back and forth between two magnets of the same polarity. And so, but a similar mechanism is also creating a photon. So, so the subject of what a photon is, people just don't explain it. They say it's something traveling through an ether. Well, if you have an atom, you have to explain how the atom pushes on the ether in some way to create the whatever it is, the compression that's going to end up moving through the ether, the vibration, the kinetic ball. But how did it push that first kinetic ball? How does it hit the ether? And how do you explain how it hits it without losing? How can it possibly move something in the ether and lose mass? If the ether takes care of all the perturbation stuff, why would the atom lose mass? And we know that atoms do lose mass, that they lose something, not nothing, when a photon leaves. It's a real piece of them. Photons are real parts of the atom, and the atom can only lose so many of them and it falls apart. You can't just give them away. And so they don't really have an explanation for that. Or even when the bigger thing, like an electron, even more obviously a piece of matter, when one of those leaves, how is that an ether perturbation when there's an actual physical deficit inside the substance? I mean, there doesn't seem to be any rational conservation law obeying if you can say that movement destroys matter in some way. Somehow it banged into the ether, and then that made the electron disappear, and a new electron was created in the other atom where the ether pushed a piece of ether into it. I mean, you know, it doesn't make much sense. I mean, you could say, okay, the electrons are an atom over here, and the electron pops into the ether, and then it stays right there, and a bunch of new electrons just go across, or, you know, it just doesn't make much sense. The ether would have to be an electron ether. Well, this is what regular physics does. They create a field for everything, so everything has its own field. You know, electrons, nuons, gluons, muons, they all have their own fields. And maybe that's how they're thinking, that you just push something into the field, and then the field has a whole bunch of them, and it just bounces through the whole field, and then a new one pops into the new atom. But why wouldn't you just go with the simple answer, which is the little bit travels from point A to point B in a straight line at a velocity? Seems to me the way to go. All right, so this video will have to do. It could be more provided. I'm just saying there's lots of. I'm not saying there's lots of. There's probably only a few ways you can possibly model this stuff to make it work. But there are ways, but they all have to be tested, and they all can have flaws, and they all have some place where it breaks down. And so there's a lot to get into, a lot of the complexity. Even though they're simple models, you can make them really simple. There's a lot of experiments. There's a lot of facts that they have to fit, and it's compiling all of those facts and recognizing that this is the list of things it has to be able to do. You know, that everybody sort of has failed at doing. You know, so I will try in the next video to be more precise. I mean, I tried to get to it with some of this stuff on the conductors. I mean, the conductors are really important. The fact that the charge does polarize the surface of the conductor in both directions, you know, this way and this way, lengthwise and around the circumference, is a really important fact. So anyway, yeah, I'll leave it at that. A temporary video. Better video to come, hopefully, on the same subjects. Like I said, I shouldn't have combined them. They're all kind of different subjects, but they all got related in this conversation. And then, but there was just no resolution. So I guess the point I'm trying to make is, yeah, that we have to find some way to communicate. So the problem is they have, whatever, 5 or 6 people in this room, and they all talk from their perspective. So they all talk through their theory. And so no point gets resolved because everybody just keeps changing the subject to their point of view. And so nothing gets, you can't get anywhere in these arguments because nothing gets resolved as what actually happens when, say, sound travels. And they should get, I guess, to those basics and see if they could agree on the actual physics of what happens when sound moves through the atmosphere. And they don't seem to even get that far in terms of having any kind of containment to the subject. Anyway, whatever. Not the best video. You'll have to do, though, for now.